We shall take a look. All right. Okay. Well, it's week 4, and we're looking at our second lecture in week 4. And we are talking about classification methods. So on Tuesday, we looked at the Bayes classifier and the naive Bayes classifier and how it works for classifying stuff. Okay? And that was a probabilistic classifier. This one, we have the k nearest neighbors classifier, and this is the algorithm. This is how it works, and I'll show some illustrations. But there's pros and cons to the k nearest neighbors algorithm, and there's kind of specific cases where it works better and things where it gets thrown off, and so. We'll talk about that. I didn't write it down, but we'll see. Okay, so with the k nearest neighbors classifier, you have this training data, and the training data is labeled with classes. Okay, so you need. It's not a clustering algorithm. Clustering, the data comes in and they're not labeled. It's a classification algorithm. The data comes in and it is labeled. So we already know whether something belongs to class A, or if something belongs to class B, or something belongs to class C, or something like that. Okay? And then when you get a new test case, it comes in, and then number one, the first thing you do is you compare this test case to every single case in your training data. Okay? You measure the distance. Usually we use Euclidean distance. You measure the distance from your test case to every single other data point that you have. And that step, depending on the size of your data, could be very computationally expensive. So if you have maybe 100 data points, this will be quick. You have to measure the distance from your one point to 100 other points. Sure, no problem. Okay, but if you have 1,000,000 entries in your database or in your data set, then your test case, you have to measure 1,000,000 distances. Okay, and so that could take a long time to do. All right, but once you do all of that measuring, then you sort them by distance. Okay, so you have the shortest distance at top, longest distance at bottom. Okay. And again, depending on how many data points you have, the sorting itself, could be computationally expensive. But I mean, sorting algorithms are generally pretty quick these days, so not to worry. And then you will select the observations with the smallest distances, the k observations with the smallest distances, or this is where the nearest neighbor's name comes from, is that you select the k observations who are the closest or the nearest neighbors to your test case. And then, and basically each of those neighbors gets a vote, and the class with the highest representation will be your selected class. All right, and so how do we pick the k? Generally you use cross-validation on your training data to kind of estimate the number of errors you would get in a new test for new test data. And, of course, cross-validation assumes that your training data looks kind of like the population. And if that's a bad assumption, then everything's going to fall apart. How do we deal with ties? Okay. Well, one is we try to avoid ties in the first place. So if there's only 2 possible classes, then as long as you pick an odd value for k, there will be no ties. The only exception to this would be if you have 2 points that are the exact same distance from your test case. And I guess depending on the data, it is possible to have two points in your data set that are exact same distance from the test case. That it won't happen if you have continuous variables, but if you have discrete variables, it could happen. And then, so then if you do have a tie, if k is even, or if there are more than 2 classes, or like I described, if you have 2 observations where they are the exact same distance, it's possible to have a tie, and then there's just different strategies for how to resolve this. One is you just designate this as unclassified. You say, well, I'm not sure if it's Class A or Class B, so I'm not going to pick sides. Okay. You could also switch to your one nearest neighbor. You can also decide to select randomly among the top tied groups. So among the, if you have Class A, B, and C, and A and B are tied, then you can just randomly select, flip a coin between A and B. Okay, and then also you can say, well, among the top tied groups, then you pick like a smaller K or a 1. Okay, then you kind of select the one with the closest neighbor. You'll say A and B are tied, but group B has an observation that's the closest, and therefore we're going to go with group B. Okay. All right, so let's take a look. For my training data, I just have some data generated by the random multivariate norm, and this is what our data looks like. So I've got some red points and I've got some blue points. And the question is, if we have a new test case, is it going to be the red class or the blue class? Okay, and so looking at this, this is kind of what it looks like. And one thing about k-nearest neighbors, and I didn't put this, but k-nearest neighbors works best when you have numeric predictors. Okay, if you have categorical predictors, k-nearest neighbors, you can't really use it. Okay, or you have to think about it, and you have to make some choices about how to use something with a categorical x variable. And I guess I can illustrate that separately here. Okay, but here this is our training data. So I've got x1 and x2. Those are both numeric, and we've got red and blue points. And let's say I put an observation right here. An observation right here. Do you think this is the red class or the blue class? What do you think? Okay, so I intentionally picked one that's a little bit, a little unsure, right? Like if we got rid of this 1 point here, it would seem like it should be blue, okay? But now with the inclusion of this one red point, we're not quite sure. Okay, so anyway, the first step is to measure the distance from this test case at 0, -1 to every single other data point, okay? So I've drawn kind of these lines representing these distances, right? Now you might say, well, that seems silly. Why would I? Obviously, this point is far away. Why do I need to calculate the distance to this 1 point, okay? Well, in 2D, it's very easy to spot distances. Our eyes can easily recognize, like, oh, these two things are far away, these two things are close, okay? But what if this data exists in 5 dimensions? Okay, now we can't even, it's hard for us to kind of comprehend visually what distances look like in 5 dimensions, or 17 dimensions, or 25 dimensions, right? Sure, 2D and 3D, we can judge distances, but in higher dimensions, it's hard for our brains to comprehend distances, or to even kind of evaluate. And so, and the computer doesn't have, eyes and a visual recognition. So it just sees a whole bunch of numbers. And so we just have to ask, all right, go ahead and compute the distance in, the Euclidean distance to every single other point. All right, so anyway, we've calculated these distances as represented by these lines here. And then what we're going to do is we sort them and we say, okay, what is the one nearest neighbor? So if I choose k = 1, who is the nearest neighbor? It is this one red point. And I've drawn a circle to show you that there are no neighbors that are even closer than this one, okay? So if this is the one nearest neighbor, this point would get classified as being red, okay? Because the nearest neighbor is red, this point gets classified as red, okay? What about if I choose k equals 3, all right, these are the 3 nearest neighbors, and again, I've drawn a circle to show that, yeah, no other neighbors are closer. And so here we have, out of the 3 points, 2 are red and 1 is blue. So it still gets classified as red. Okay. At k equals 5, though, at k equals 5, we have 3 points that are blue and 2 points that are red. And therefore, this, if you had k equals 5, this test case would get classified as blue. And at k equals 7, okay, we have 4 that are blue and 3 that are red. And it looks like this one was really close, but it's just ever so slightly farther away than this point, okay? And so these are the 7 points that are closest to our test case, and 4 of them are blue and 3 are red, and so therefore it would get classified as being blue. Okay, and that's kind of how it goes. So you just measure the distance to every single other point, and then you count how many values belong to one class versus another, and whichever one wins is the one that gets classified. Okay. All right. Here's another test case. What do you guys think this test case would be? Red. Okay. For k equals 1. What about k equals 5? Still red, right? It seems pretty clearly on the red side. Seems pretty clearly on the red side, but we'll go ahead and we'll just check it out. So again, measure the distances. And so, this is why, so I would say k nearest neighbors is not a preferred algorithm, okay? It's, I think there is an appeal to its simplicity and easy to understand nature of it. And depending on the data set, it can work well, but in situations where you have big data, okay, or very high dimensional data, it gets this step, calculating the distance to every single other point, can become very computationally expensive, right? And so this is a toy data set. I've got 30 data points, 50 data points. How many points do I have? What did I generate? 24 data points, 14 Class A and 10 Class B. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I've got a total of 24 data points. So it's very simple. Okay, all right, so at k equals 1, we have 1 red point. That's the closest. At k equals 3, I have 2 red points and 1 blue, so it's still red. At 5, I have 3 red and 2 blue. At 7, I have 4 red and 3 blue. So all of these, it gets classified as red, okay? So all of these things choose red, and that's what we have there, okay? Remember when we talked about lasso, we said you should scale your data? Generally, you should do the same thing with k nearest neighbors, okay? So, because for example, let's say you measure, I don't know, for one thing, but then, well, it gets complicated, right? Let's say you wanted to compare 2 people, right? And you were going to use height and weight to kind of decide how similar people are, right? So again, but how do you compare these things that are on different scales, okay, or different units of measure? And this is something that gets that makes k nearest neighbors difficult, right? So let's say you have a couple people, and you're comparing their heights and their weights. Okay, so let's say 2 people have the same weight. Let's say they both weigh 150 pounds, but one person is 5'5", and the other person is 6 feet tall. Okay, so there's a 7-inch difference, but they both weigh 150 pounds. Okay, so that's one scenario. So you have so basically your distance is 5 there. Okay, and then you have another. Then you have 2 people who are the same height. Let's say they're both 5'10", but their weight is 5 pounds apart. 150 versus 155. Okay. According to k-nearest neighbors, the distances between is the same. Okay, the person, person A. Let me write this down. Okay, just so we can kind of keep track of all of this stuff, because we're just looking at the distance of 5 and 5, right? So you have to ask, does this make sense, right? So always, one thing, we're teaching you like some of these algorithms and stuff. And one thing that always kind of kills me is that when I see students, or not even just students, professionals, real people, like applying these algorithms blindly without thinking about like, let's pause and ask ourselves, does this kind of comparison, does this thing even make sense in the first place? Okay, so let's say we have person A, we'll call this person Adam. Okay, so we have height and we have weight. Height in inches, weight in pounds. All right, and I apologize to our international friends who don't who hate American customary units. It's like the worst, right? Okay, so we'll say Adam is 5'5", so that is 65 inches. Weight is 150 pounds. Okay, we'll have Bob, who is let's just do 5'10". Let's keep everything 5 apart. So this is 70 inches and weighs 150 pounds. Okay, and then what's Carl, C, okay? This person we'll say is 5'10", so 70 inches, and weighs 155 pounds, okay? If you did k-nearest neighbors, and you say, who are the nearest neighbors to Bob? Bob's nearest neighbors. Or here, let me just make Carl 156 pounds, okay? 156 pounds, okay? Bob's nearest neighbors, it would say Adam is closer because the distance is what? 70 minus 65. So we're looking at Bob and we're comparing to Adam, okay? So we're looking at 70 minus 65 squared plus 150 minus 150 squared, right? And so this is going to be 25, okay? If we look at Carl, this distance is 70 minus 70 squared, so 0 squared, plus 150 minus 156 squared, okay? 36, all right? However, I would argue that Carl is more similar to Bob than Adam is to Bob, right? So this, what's the conversion? Inches to centimeters conversion, just so we can. All right, so if I say this person is 65 inches, okay, so this is around 165 centimeters. And then here I've got 70 inches, 178, okay? For centimeters, okay. And then pounds to kilograms. All right, what do we have? 150. Okay, so this is 68 kilograms. It's 70.7 kilograms. Okay. Let's see. Okay, well, and so here you can see that changing the units also here changes dramatically. Also changes who's closer, right? So so Bob's nearest neighbors with U.S. units, okay, Adam is closer because his height difference is 5 squared, 25, versus Carl's difference, the difference in weight, 150 to 156, 6 squared is 36, right? But if you use metric, okay, so Adam to Bob distance is, what's Adam's to Bob's distance? 165 to 178, that's 13 squared, right? 178 minus 165 squared plus basically 68 minus 68 squared, so we get 13 squared, 169. Okay, and then we have Bob to Carl. Bob to Carl, we have 178 minus 178, so that's 0, and then over here I do 68 minus 70.8 squared. What is that? 2.8 squared. What's 2.8 squared? $7.84. Okay, so you can see how changing units dramatically changes like who's closer, right? And I would say that you know, if we're comparing people, okay, I would say Bob and Carl are a lot more similar. These two people are the same height, and their weight difference is what, 6 pounds or 2.8 kilograms. Okay, so not a huge difference there, in my opinion. Okay, whereas Adam and Bob, even though they're the same weight, they have a 5-inch difference or a 13 centimeter difference, and I would say that's a bigger difference as far as comparing two people or something. You know, I don't know, okay? But as far as the algorithm goes, it just sees numbers. It doesn't see the people. It doesn't know the context of these numbers and what's considered high or low, and you know, is a difference of 5 big or small, okay? And as far as height goes, a difference of 5 inches, kind of a big deal. As far as weight goes, a difference of 5 pounds, not that big of a deal, right? A person isn't going to go from 1 week to another week and have a 5-inch difference, right? Whereas a person might encounter a 5-pound difference in their weight from 1 week to another, right? And that's, I mean, not great, but it could happen, right? Somebody could change weight about 5 pounds within a week, whereas somebody changing 5 inches of height or 13 centimeters in height in a week, we would say something miraculous or strange happened, right? Because, you know, I think it's literally impossible for someone's bones to grow that much within a 1 week time frame or something, okay? So anyway, when we look at these numbers as people and we understand the context behind them, we recognize, okay, these distances and things like that. So you would need to come up with some kind of scale that puts these units on a similar footing, where we say, okay, it makes sense when you have, you know, a 1-inch difference in height, that's equivalent to this much difference in weight or something like that. And so, you know, a lot of times scaling and normalizing your data to have kind of mean 0 and standard deviation 1 or something, that makes sense, okay? But not always, right? And so it's important to kind of have that, right? In these toy data sets, sure, we're just using the same distance. But if I kind of plotted these and we say who's more similar and more similar, we got to kind of keep that in mind. Okay, does that kind of make sense what I'm trying to say here regarding distances? And so yeah, don't just blindly apply this. Okay. Oh, and so the other part is, okay, what if you had a categorical variable? Okay, categorical variable, right? And so let's say, I don't know, you had some other attribute. Okay, like hair color, okay? Now this gets complicated, right? So we say hair color And let's say we have brown hair, blonde hair, brown hair, or something like that. Okay. Well, I guess. Okay, we'll say brown, blonde, and blonde. Okay. And so the question is, what's more important? Okay. Is a difference between blonde hair versus brown hair. Like, how do you scale that difference, right? If we had to say a difference between someone's brown hair versus blonde hair, because again, we're trying to ask who is more similar to each other, right? We're trying to come up with some measure of distance, okay? So we have brown hair versus blonde hair. How do we measure that difference? Like, how do we put that on the same scale as, comparing someone's height or comparing someone's weight? Okay. Now, if we just turn this into like 0 versus 1, okay. Well, you can't actually do hair color and do 0 and 1. You'd have to turn them into dummy variables. Okay. So you'd have brown hair, 0, yes or no, use brown hair, blonde hair, yes or no, black hair, yes or no, okay? Because if you have brown hair, blonde hair, I guess you could put them on a scale and say black hair is more than brown hair, which is more than blonde hair, and we're like measuring, I don't know, the density of hair pigment or something, okay? Because, maybe it makes sense to kind of put it on some kind of gradient scale, right? You go to the hair coloring aisle at Target, and they're, I don't know, are they arranged by like light to dark and stuff like that, and they might put some kind of number or something? And I don't know, like, what happens if you have to go to another brand? Like, is there like a universal color conversion? They should have some kind of universal standard, right? But okay, so that way, like, if you went to another part of the country where they sell like different brand, or another country and they sell different brands, you can say like, oh, this is the hair color I need to get because it's a universal color of whatever. And but then I guess it would be multi-dimensional, right? Because you'd have kind of like super light blonde hair on one side and black hair on the other side, and brown, dark brown, and lighter brown, and something like that in between. But then you also have like shades of how gray. And so, okay, anyway, I'm overthinking this fictional hair coloring system. Well, and then there's like what do you do about like somebody who wants purple hair? And okay, never mind. All right. Well, anyway, but the idea of like, okay, well, here I got a 0 versus a 1. So actually we should just do blonde versus not blonde, and brown versus not brown, and right. And so you might have like, you might try to turn these into dummy variables and 1s and 0s, but then numerically, what is the appropriate distance to put these things on, right? Like, numerically, is this difference between blonde and brown hair, or blonde hair versus not blonde hair, and brown hair versus not brown hair, is that equivalent to a 5-inch difference in height? Is that equivalent to a 2-inch difference in height? And these are complicated questions, or these are questions that are kind of impossible to answer, really, right? Like, if you said, okay, we need somebody to play this historical character, right? And you're like, okay, well, let's try to figure out who's the closest match using these metrics. What are we going to judge most similarly, right? And I'll say, oh, you know what? If we need to pick somebody who's going to play, this character, what are the most important kind of things to, pick in some database of of features and stuff, right? And we can say, okay, do they have the same height? Is that even important? Do they have the same weight? Is that important? Do they have the same hair color? Is that important? And some of these things we can kind of like, we can give them a wig and take care of, and other things, I don't know, right? So, Do you pick somebody with from right? And then there's a whole bunch of like intangible things, right? So like I don't know. I think sometimes we hear like, oh, this person is going to play Marilyn Monroe, and we're like, oh, really? And then you say, oh, okay, I guess that could work after you watch the video or something. But just how do you measure something like that, right? And basically, you can't always just throw it and say, oh, it's just a data problem, and we can just ask the algorithm to solve for us. So you got to kind of think about this. What was I saying? All right. Oh, okay. So here I just kind of want to show like what happens when you change k, and as far as drawing these boundary regions. Okay. So I've drawn these boundary regions. How did I draw these boundary regions? The way this thing works is I have our same data set. Okay, the red points and the blue points. I think it's the exact same. So if you kind of if you look at where the red and the blue points are here, it's the exact same locations as here. Okay, these are the same, I think, right? Okay, same exact training data between red and blue. And now you see a whole bunch of grid, a grid of points. And basically the way this algorithm worked was I looked at every single one of these points in the grid, and I said, okay, if I have a test case right here, and I did k equals 1, who is closer? And it says, oh, the blue is closer. Okay. Over here, this grid dot on the grid here says red is closer. Right, and that's what's going on here. And so we kind of created this whole grid of points, and we said, all right, which one's closer? And we get this is what we get with k equals 1. We get this kind of this boundary here. Here it is with k equal to 3, and here it is with k equal to 5, and here it is with k equal to 7. Okay. And basically what happens is that with k equal to 1, each individual point in our test case has a lot of influence. Okay. Whereas with k equal to 7, each individual data point in the test case, in the training data, has less influence because the test cases take into account 6 other points. Okay, 7 points total. And so as far as the bias variance goes, k equal 1, small k will be high variance, lower bias. And as k gets bigger and bigger and bigger, now you'll decrease the variance and increase the bias. Okay, here it is with a larger data set, more points. So what happens with k equals 1, every single one of these data points, so we look at this and we say, okay, well here's a couple blue points that look like they're in red territory. Okay, or here's a red point that's clearly in blue territory. And each of these things get their own little exclave or enclave of influence. Okay, so and I always forget which one's which one's an exclave and which one's an enclave. It's it's like when you have like there's what is it? I always forget. I have to look this up every single time. Maps.google. So like in Europe, there's that piece of Russia that's detached from the rest of Russia. Do you guys know what I'm talking about? We're going around the long way to Europe. Okay. So this part right here, Kaliningrad. Okay, so this is Russia, right? And it's bordered by Poland and Lithuania, but it's Russia. So what is Kaliningrad? Kaliningrad is a semi-exclave. Okay, so it's an exclave, right? So you get is the capital of Kaliningrad Oblast, a Russian semi-exclave sandwiched between Lithuania and Poland. Okay, so yeah, an exclave is basically a piece, you know, like if this was blue country, okay, this is like they have like an outpost in enemy territory, okay, or something, right? And basically every single dot gets to set up like their own little zone of territory, okay? But then when you have k equal to 3, okay, these blue dots don't get to set up their exclaves anymore and stuff like that, okay? And so here's k equal to 1. You can look at the boundary. K equal to 3, k equal to 5, k equal to 7. The border doesn't necessarily get smoother, but it's now less influenced by just lone stragglers here and there, okay? And so that's what we see with k equals as k increases. All right, and that is, and so here it is with k equal to 20. I should have not picked 20. I should have picked like 21. And we get, some kind of straighter line border here, okay? That is, I guess that's all I have to say about that for k nearest neighbors. It's a pretty basic and simple algorithm. It's fine. But again, because for big data, because it requires you to calculate the distance to every single other point, it can become very computationally expensive and perhaps might not be your preferred choice. Let me give you your first view quiz answer today, which is the letter D. D as in dog. D as in dog. I will say a student later came back to me after graduating and said they had a job interview, and one of their interview questions was, can you just explain how the k nearest neighbors algorithm works? And they just basically, I guess they had studied and they basically not read, but told them this. Yeah.
I was wondering what you think about weighted k nearest neighbor. Like, do you think it would be better or worse than just normal nearest neighbor?
Yeah, so I mean, anytime you add more information, so weighted k nearest neighbors is basically you provide some kind of weight to the points, and you say like the nearest points, like if we were voting here, so weighted k nearest neighbors says the nearest points get like more voting power than the farther away points, right? The farther away you are, like we're going to give your vote less influence as far as whether somebody should be red or blue. Like you're going to take like your sister's advice more heavily than like your third cousin's advice type of thing, okay? And so so that's the idea of weighted k nearest neighbors. And so so you're basically bringing in, I guess not more information, but just like adding another dimension to it. And I guess the answer is it depends. Does it, when we talk, well, first of all, you have to ask, does it make sense to even, can we measure distance? Okay. And, in the case of like hair color, blonde versus not blonde and brown versus not brown, like, can we measure distance? And the answer is I'm not sure. Okay, so you have to kind of you have to ask that question first. Can we measure distance? And then the next question you ask is, does it make sense that we're using distance as a way to measure similarity? And if we say, okay, this distance is closer, then they are more similar. Like, okay, maybe that makes sense. And then k nearest neighbors could work, and then you can say, okay, well, should we give nearer distances more voting power? And maybe the answer is yes, and maybe the answer is no. So weighted k nearest neighbors is not quite k equals 1, but it's gonna fall more on that side of higher variance, lower bias. Okay, so there all of these things, like what should I do is really like, where are you on where do you feel is the best solution on the variance bias kind of spectrum. So that's what we have. All right, let's talk about another. Did I give you your first view quiz answer? First view quiz answer is D. D as in dog. D as in dog. Okay. Support vector machines. Let's talk about this. The math for support vector machines gets really complicated, and in fact, we don't even solve it. We just say, all right, this is what we thought about, and we get to a point where we can ask the computer to solve it, and then we just leave it at that, okay? And we don't actually kind of solve it. And it gets solved computationally using, I guess, quadratic programming or something. But anyway, we start off with this simple version called the maximum margin classifier, and we have maximum margin linear support vector machine, and then we just kind of make these things a tiny bit more and more complicated until we get to something called kernelized support vector machines, which is kind of what we think about when we do support vector machines. Is we work with a kernelized version of it, and I'll have to explain what a kernel even is in the first place. I touched on this in 101C, but here we'll kind of dig in a little bit more on the effect of some of these parameters here. Okay, so the maximum margin linear support vector machine only works if your data is linearly separable. If we can draw a straight line that's going to separate our two classes, and we try to draw kind of two parallel lines like a highway that's as wide as possible to kind of separate our two classes, right? So here, this is blue and red, and we want to draw a highway. We want to draw the widest possible highway, and that will form the boundary, okay? So I'm going to just kind of draw. So here's one possible highway, right? I can draw a road, and this straight line, okay, separates blue from red, and it has 100% correct classification, but the width of this road is kind of narrow. But if I change the angle of this, right, if I, instead of going nearly straight up and down, if I angle the road, I can make it wider. And if I do this, it gets the width of kind of this road or this highway or this, we call them linear, these linear, I guess in here it's just two lines, okay? The distance between these two lines, these parallel lines, is a little bit more, okay? In a higher dimensional setting, if we had three-dimensional data, they won't be lines, they will be planes, right? I would have red dots and blue dots floating around in space, and I need to draw these parallel planes in 3 dimensions to kind of separate them, right? That's kind of the linear shape there. And then in higher dimensional space, again, harder to imagine, you have a hyperplane, okay? You have a hyperplane that separates your red dots floating around in 4-dimensional space and your blue dots floating around in 4-dimensional space. You have some kind of linear hyperplane. And if we draw this set of parallel lines or parallel hyperplanes, this one has the widest margin. And again, I could even pick this one. So even this line separates red and blue successfully, but it has a much narrower margin. So this is not going to be the preferred one, okay? So we would want this, not this, and probably not this, okay? So yeah, support vector machines or the maximum margin and classifier says, yeah, pick the one that maximizes the margin or the width of the road here, okay? And that's just, it's defined as the perpendicular distance from the decision boundary to the edge of the margin, which is the closest points to either side. So we look at like, okay, these dots end up on the line, okay, and we're going to look at the perpendicular distance. This dot ends up on the line. we're going to look at the perpendicular distance there. And these points that define the decision boundary, these are called your support vectors. And the reason why they're called the support vectors is because once we've established this line only depends on the location of these 3 points. Okay? And like if I added a blue dot out here or a red dot out here, right? So if I take a dot and I add it over here and it's a minus sign, or if I take a actually I don't know how to change the color of my pen, but basically if I add any points over here, it doesn't matter. It's not going to change the location of this line. Okay, so the location doesn't change as long as those 3 support vectors remain in the same position and remain closest to the boundary. Okay, so here is in purple, I have the distance of the width of the margin. Okay, perpendicular distance from one parallel to the other, and this one has a much smaller margin. Okay, and so how would we maximize this? Okay, well, if we have some training points, okay, what we do is we label the points. We give them a numeric value of +1 or -1, +1 or -1. So if you have, the red class is -1, the blue class is +1. And we want to measure the thing. Now, you define a hyperplane using weights W. Okay, you have W, which will be a weight on x1 and x2. And so when you do W transpose x, you're multiplying W transpose x, and you say W transpose x equals 0. That's going to define this middle line here. And then we say W transpose x minus B is going to be any line that's parallel to this line. So W transpose x equals 0 is going to form this middle line here. And then you do W transpose x plus or minus some kind of constant B, and plus some constant B, and that's going to allow for just basically parallel lines to this. Okay. And so, any kind of hyperplane can be written as W transpose x minus B is equal to 0. And that's what we have, right? So we're going to say, all right, W transpose x minus B is equal to 1 for anything on the positive side of the margin, and W transpose x minus B is anything on the negative side of the margin. And we'll let x1 and x2 kind of be the closest points from each class. And so this is what we have, right? So we have W transpose x plus B equals 0. Is right here. And then, and then I've got W transpose x plus B minus 1 will be dots along this plane, plus B equal to +1 will be dots on this plane, right? So this is basically just saying W transpose x, you can just kind of make parallel lines to this, and this is what we have here. And if you have a new point that ends up on the boundary, it would end up equaling 0, and it wouldn't get classified as either +1 or -1. So what we do, right? So this purple line is basically equal to the vector of this purple line is equal to our W vector. And if we dot that with the vector x1 minus x2, okay, we project this onto kind of the vector for the distance between x1 and x2, right? And we say, all right, well, what is this going to end up being, right? So if we have, so the vector x1 minus x2 is basically this blue vector. This is the vector that joins these 2 points, the 2 points that are kind of that separate the plane. All right, and if W is a vector perpendicular to the boundary, then W divided by the norm of W is going to be the direction. And we want to know the direction of this vector, this purple vector, right? And so we're going to just arbitrarily define and say the width of this margin is going to be 2 times gamma, okay? And we could have just picked gamma, but we're going to just arbitrarily say it's 2 gamma. And if we do this, then we'll say the width or the length of the margin, 2 gamma, is equal to basically W times a vector of length 1, but W over the norm of W, dotted, or W transpose times that vector x1 minus x2. And we want to maximize this, right? So if we say, when we do W transpose x1 is on, this is going to be equal to plus 1. It's this dot over here. And W transpose x2 plus b is going to equal to minus 1. Okay? Then we can kind of do this, and we'll say, all right, I get W transpose x and minus W transpose x2, right? And we're going to say, okay, I can add a constant b to both sides, and now I get this is going to equal 1, and this is equal to negative 1. So this whole thing ends up being 2 over the norm of W. And so we get that distance, gamma, equal to 1 over W. And we want to basically, we want to maximize this thing, which is equivalent to minimizing W, the norm of W, I should say. All right, so maximizing that distance gamma now becomes equivalent to minimizing the norm of W. And we want to minimize this, but it is subject to a constraint that, that whatever we pick for W does classify everything, that everything that's on the positive side gets classified as being greater than or equal to 1, right? So, because when I do this, I'm basically getting some value over here, and they need to be higher than 1, and these values over here need to be more negative than negative 1. So we're going to do that, and we can say, all right, everything W transpose x minus b has to be greater than positive 1 for anything that's classified as positive. And so we can do t times this, and then and I can also combine it with this thing. So we can turn both of these things into just one constraint by kind of multiplying the two together. And we're going to say that this product, because for the negative values, this would be negative and this will be negative, and so it's going to be greater, a positive value. So we can kind of put these two constraints into one equation. All right, so anyway, we're going to try to summarize this subject to constraint. I'm going to kind of skip over this because I don't feel like getting into it. But basically, maximizing stuff or minimizing stuff subject to constraint, you use like Lagrangian terms. And then when you do this product, you now have a whole bunch of these alphas here. And so the next slide is like just a huge mess. So just ignore it, okay? Okay, because you get all of this stuff. And oh my gosh, this was such a pain to typeset. And I think I got the subscripts correct, but there might be a typo in here. I don't know. All right, but basically, this is what we have, and you get it kind of into this form here, and you can also read the textbook. It talks a lot about this stuff. And then it leaves you with this very unsatisfying conclusion or sentence. And it says, oh yeah, by the way, there's no closed form solution. So it's like, it leads us through all of this. And then it says, oh, there's no closed form solution, but you can find the optimum via quadratic programming. So I was like, okay, well, what's quadratic programming? And it was a huge pain to try to read through it, and I never fully understood how it works. And R has a quadratic programming function, but it's also quite obtuse. So I'm not gonna I'm not gonna get into it. But I think just maybe I feel okay with it, that I don't fully understand how the quadratic programming works. Just because I guess conceptually I can understand this, right? We just want to pick two parallel lines that are, we're going to maximize the distance, and we have a method to do it, right? Visually, it's very easy to say, okay, these two things are going to maximize the distance. And apparently, if you have a whole bunch of data points, you can establish what these two parallel hyperplanes are going to be just by kind of going through every single data point, okay? But you're going to have a whole bunch of these values alpha that ends up coming in here, and you're going to have alpha is equal to 0 if that observation, if a particular observation does not have any influence on the final result, and then you have alpha equal to some value when it does have influence, okay? So the final kind of solution for W is going to be some product of alpha multiplied by the values of X. And so basically, we would have, so in our case, okay, why is this shrinking on me? Let me open up another window. So for our final solution here, for establishing what this is, this vector is going to be determined by kind of taking the sum of alpha times some weight, okay, or yeah, some weight alpha multiplied by these three vectors. Okay, these are the three vectors. When you kind of add them together in some form, you're going to get this perpendicular line, okay? Versus these points will all have alpha 0 because they have no influence on what this W finally ends up being, okay? So we're going to just kind of get, some point here, okay? So we just get alpha times, your x's and some weights of alpha here for those particular x's, and then the alphas for these other points are all going to be 0. And apparently our algorithm can kind of figure out which x points get weighted 0 and which ones don't. We can kind of loosen this up, all right, by saying, you know what, we can allow for a soft margin. Okay, so a soft margin says, okay, let's solve for this. Okay, but you know what? The alpha is going to be, there's going to be kind of a hard upper ceiling on this. When we solve, we're going to put an upper ceiling on this, and this will allow for points to kind of fall within the margin. So we don't need to have data that is perfectly linearly separable. Okay. And so, we're going to put a limit on how much a single point can influence defining the boundary. Is basically what we're going to try to do here. So the idea here being, I don't know if I can draw on this. Like if I put, okay, I can't. Like if I put an observation, say right here, okay, this point now falls on the wrong side, and my boundary would have to separate the red from the blue And I'd probably, or better yet, let me put a dot over here, okay? A plus dot right here, okay? If we do that, then our boundary has to, can't allow for this to end up on the wrong side, and so our boundary would have to look something like, it's really hard to draw a straight line on this. It would have to look something like that, okay? And that's kind of non-optimal. Is there no undo here? I don't know how to use this, I guess. Okay, so I can, on the other hand, even if I do have a point right here, a new plus point right here, we can say, you know what? I'm fine with it falling on the wrong side of the boundary, okay? I'm okay with it falling on the wrong side of the boundary. And we're going to just keep this, and we're just going to kind of ignore this one point, okay? That's what a soft margin is, okay? A soft margin says, you know what? We're going to draw this line, and I'm not going to adjust the line if one point ends up falling on the wrong side, okay? We don't like it, but we're not going to redo everything here. We can, and so that's kind of this idea of a soft margin. And we're going to kind of further complicate this by introducing kernel functions, okay? So with support vector machines, we said, all right, we're going to find our linear boundary by kind of maximizing this thing, which has all of these values, but it comes down to figuring out what is the appropriate weight to put on the, how much influence do each of these points in our data set have, okay? And if we're able to figure out how much influence the points in our data set have, we can establish what this optimal boundary is going to be. And we have this inner product between x, we're kind of measuring how we're taking these inner products between every 2 points in our data set, xm and versus xn, okay? And we kind of go through basically every single possible combination between all of our x's, right? So we're basically comparing, okay, this dot versus this dot versus that dot, this dot versus that dot, this dot versus that dot, and we're kind of, there's this big product between them. Every single dot compared to every single other dot, taking inner product, and as we go through it and try to optimize this, we're going to say, all right, these are the ones that are most important, and we put weights on them. When you have an inner product, we can also we can replace this inner product with a kernel function that applies to every combination of xm and xn. So we're going to compare every point to every other, but the way we compare them is not just not going to be the inner product, but is going to be we apply a kernel function. So what is a kernel function? Okay, a kernel function applies a transformation and then takes the inner product. So we take our original, we take your values in one point m and values in another point n, and we take the dot product between them, okay? Over here, we take the values in point m, we apply a transformation function, phi, to it. Here's a value in n, we apply a transformation function to that, and then we take the dot product, okay? So it's basically just taking the dot product after you apply just like some kind of transformation to it, right? And so, if you have your, so a silly version of something like this, right, is, we could have taken dot products between, these two people, Adam and Bob, or Bob and Carl, and we would have done like, 65 times 70 plus 150 times 150 or something. Or we could have also applied some kind of transformation. Here we just multiplied by a constant to convert them from inches to centimeters and pounds to kilograms. We applied a transformation, and then we could take the dot product. All right, so that transformation is as simple as this. You can apply more complicated transformations, which is what we're going to do, where we're going to convert our values from 2D into 3D. We apply some kind of transformation function. And so here is just a very simple transformation function where my data exists in 2 dimensions. I have x1 and x2. I have 2 coordinates. And I'm going to say, after I apply this transformation function to it, now my data is going to exist in 3 dimensions. We're going to basically keep the x1 coordinate, we'll keep the x2 coordinate, but I'm going to add a third coordinate, and that third coordinate's value is going to be x1 squared plus x2 squared. Okay, so we're applying a transformation function, and we're going to apply it here. And when I do that, now I'm going to say, okay, now my data exists in a higher dimensional space, and we're going to take the dot product there. Okay, so let's say I have 2 points, 1, 1, and 5, 1. Okay, I could take, instead of just taking the dot product between 1, 1, and 5, 1, which would give me what, 6, right? 1 times 5 plus 1 times 1. I'm going to transform this into using this function phi. So function phi is going to take my 2-dimensional point and make it 3-dimensional. So the point 1, 1 is going to become 1, 1, 2, right, in 3D, right? The last point, the last coordinate of this point is going to be x1 squared plus x2 squared. And then the point 5, 1 becomes 5, 1, 26, right? So I'm adding a third dimension to this thing. And so when I take the dot product of these things, I get 1 times 5 plus 1 times 1 plus 2 times 26, right? So that's 5 plus 1 plus 52, and that adds up to 58. That adds up to 58. Okay? Is that all right? So all I'm doing is I'm just taking my data, which exists in 2D, transforming it into 3D, and I could have other kernel function or other functions maybe transform it into 4D or 5D or some higher dimensional space, and then I take the dot product of those resulting coordinates. That's all I'm doing. So do we understand how we got this number 58? Okay. So the thing is sure, we could go through this process of transforming it into 3D and then taking the dot product, but we also don't have to do the transformation and take the dot product, right? So some of these, some transformation functions will have an equivalent kernel function, okay? So the equivalent kernel function for this is you just take the inner product of xm and xn. You do xm transpose xn plus norm xm squared times norm xn squared. Okay, and if you do this, the result is going to be equivalent. Okay, so you don't have to transform the data into 3D and take the inner product. You can just leave the data in 2D. Okay, x1 and x2, but if you use this as the kernel function, you'll get the same result. So again, my data here is 1151, and if I use the kernel function directly, I get the inner product of 1151, okay? So I do 1 times 5 plus 1 times 1, and then I do the norm of xm squared, so 1 squared plus 1 squared, times the norm of xn squared, 5 squared plus 1 squared. And so I'm going to end up getting, over here is 6, and I have 2 times 26, and I get 58. All right, so here I get the result for comparing one point to another point. I get this value 58, versus over here I transformed them into 3D, and then I took the inner product, and I got the same result, 58. Okay, so all this is to say, I think conceptually, it's easy to understand this concept of taking a data point, applying a function that transforms it into a higher dimension, and then taking the inner product there, right? Whereas the kernel function, this feels a little bit stranger. Like, how is this working? Okay, well, this is just the equivalent of doing this, okay? The equivalent of transforming it and then taking the inner product. Without, this is like a shortcut where we didn't need to do the transform and do the inner product. We can just go straight to applying the kernel function, and we get the same result. Okay, is that all right? Okay, before I forget, let me give you your second view quiz answer. I haven't done that yet, right? Second view quiz answer is the letter B. B as in bear. B as in bear. Okay, so what we're going to do is we're going to use the kernel function to pretend to kind of project our data in a higher dimensional space, and then create a linear boundary. Okay, so here is a video. We probably have to endure an ad first. Jeez, it's loud. Okay, so this is an old video, but I haven't found anything better than this. It's really good. Okay, so it's hard to see right now, but there are points in red out here, and there are points in blue in here. And this exists in 2D, right? The data exists right now in 2 dimensions. And if I tried to apply the maximum margin classifier, I would not be able to do it, right? The maximum margin classifier says, look for a straight line that's going to separate the red from the blue. But, in this toy data set, all the blue points are in this circle and all the red points are outside of the circle. So I can't find a straight line that's going to separate red and blue. So what we do is we are going to take this data, which currently exists in 2 dimensions. Okay, so you can see the blue points inside and the red points out here. We're going to take the data, and then we're going to, again, this exists in x1 and x2. We're going to apply that 3D transformation. Okay, so we're going to say, okay, points near the center, which will have x1 squared and x2 squared small, will be down at the bottom. And points that are far away from the center, which will have x1 squared and x2 squared high, will end up being up higher on this paraboloid. Okay, so now the data, which originally existed in 2D, now exists in 3D. All right, that's all we have here. Okay, so the data exists in 2D and now is in 3D because we applied that transformation function. And now that the data is in 3D, we can draw a hyperplane that separates the blue from the red. Okay, we can draw a hyperplane that separates the blue from the red, and this will establish our boundary now. Okay, so this hyperplane exists in basically 3-dimensional space. Okay, so the hyperplane exists in 3-dimensional space, and it separates the blue from the red. Okay, so in 3D, it is linear, right? It's a linear plane, right? So I guess it's not even a hyperplane. It's just a 3D plane, okay? And and the shadow of its boundary now forms a circle over here. Okay, and so that's how. Okay, so that's how using a kernel works here, right? We're taking our data, which originally exists in 2D, and then we apply some kind of transformation function to get it into 3D, and then in 3D we can draw a line that separates it, and we can use that to separate our points. Okay? Yeah.
Wouldn't it almost always make a circle since the third dimension is based off distance?
Yes. If you were to use this as your transformation function, x1 squared plus x2 squared, you're always going to get either circles or basically conic sections. Okay, you'll get some kind of conic section for this. If this were your transformation function. Now, you don't have to use this as your transformation function, and in fact, we don't even really use transformation functions. We'll just go straight to the kernel function. So this kernel function is equivalent to this transformation. This kernel is equivalent, I guess I should say this kernel function is equivalent to using this transformation and applying it. But we don't actually have to use the transformation, okay? So there are a bunch of kind of these kernel functions, and you can read about this. This gives you a headache. But we have some examples of kernel functions where did it go? Positive definite kernel. All right, so here I've got, all right, the linear kernel does no transformation. Okay, a polynomial kernel will do this. We have a Gaussian kernel or radial basis function kernel. And then there's all of these other kind of kernels, the Laplacian, the Abel kernel, I don't even know, all right? So one of the most popular ones is the radial basis function kernel, which defines the kernel, the kernel distance or the kernel metric as between some point x and x prime. Instead of xm and xn, they use x and x prime. They say, okay, well take the distance between x and x prime, your 2 points, take that squared distance, so the Euclidean distance, squared Euclidean distance here, divide by some arbitrary value sigma, and then raise e to that thing, okay? This function, okay, the result of it, okay, so here, this kernel function was the result of you applying a transformation function that created this, okay? This Gaussian kernel is technically equivalent to using a transformation function that transforms your data into something, takes your two-dimensional vector and turns it into an infinite dimensional vector, okay? And it's based on the Taylor expansion for the exponential function, right? So if you remember the Taylor expansion, I don't know, what was the Taylor expansion for exponential? Okay, so yeah, if you take, so e to the x, is 1 over x over, 1 prime x squared over 2 prime, 2 factorial x cubed over 3 factorial, so on and so forth, right? So this is kind of your exponential function, and this is infinite, okay? That is, we're basically going to transform our two-dimensional data into some kind of big kernel function, okay? Or not kernel function, big kind of infinitely long thing, and I mean, you could probably do it, truncate at, 10 or something, and you'll get something very close to equivalent. And it would be the equivalent of kind of, transforming it that way. So So but we don't actually have to transform it into this higher dimensional space. We can just use the kernel function directly without bothering to transform it, right? So here is, I think this is, I use the same data set in your homework, right? And in your homework, I just drew, like, I think, just so your homework didn't end up being like 60 pages long, I think I only drew a couple example images for your next homework for you to kind of classify. But here I think I've drawn a few more, and I kind of want you to play around with some of these parameters and really get a sense for what these the parameters do here, right? So what we're going to do is we are going to use a kernel function. All right, I'll start off with a linear one, which is only able to draw straight lines, but I want you to try using the Gaussian kernel or your radial basis function kernel, which has a couple kind of parameters to mess around with. Or really, I guess it has the gamma parameter to mess around with, and then you can also mess around with the cost function, which is related to how hard or soft your margin is in the support vector machine. And I want you to kind of see what effect that has. All right, so for a linear kernel, it tries to draw a straight line that separates basically our red points from our black points, and this is the line that it draws, and it says, this is the best I can do. Okay. What if we did a polynomial kernel? Okay, so polynomial kernel. Now we can we'll have a non-linear thing. But again, it's transforming it into some higher dimension, and it's drawing a linear hyperplane, and we're getting basically the shadow of that. So over here we have a couple parameters to mess with, and this is the polynomial kernel, and this seems like it does a bad job. Okay, now this, I have the dark line, that's kind of the center line, and then I have this thinner black and red lines, and these lines are parallel in these are parallel hyperplanes in the higher dimensional space. Okay, they're not quite parallel when we look at their shadows in 2D, but in the higher dimensional space, these are actually parallel. And this kernel visually doesn't seem like it's doing a good job, but we can say, all right, well, what if I make a higher dimensional kernel? So this is in fifth degree polynomial, and this black line, even though it's like coming over here, is actually just one linear plane in 5 high dimensional hyperspace. Okay, so this is what we're getting. Again, not super great. But let's use the Gaussian kernel, the radial basis function, okay? So we say kernel equals radial, and here I have gamma equal to 0.5 and cost equal to 1. And this is the boundary that it draws. So we're looking at this line, and we say, oh, you know what? Actually, seems kind of decent as far as separating the black dots from the red dots, okay? Seems kind of decent here. And we could try messing around with different values for these kind of two parameters. Change the gamma, change the cost. So what happens if I alter the gamma? So here I'm going to keep the cost at 1. And what happens when I alter gamma? So here gamma is 0.1, gamma 0.3, gamma 0.5, gamma 1, 2, gamma 5, gamma 10. Okay? So let's so what happens if as I increase the gamma, so this is gamma 10, this is kind of the boundaries that I get. Is this high variance, low bias, or low variance, high bias? Yeah, so this falls on the side of higher variance, lower bias. Okay, and then what about over here? Yeah, this would be high bias, lower variance, and that like, where does this boundary get drawn? It's going to get probably not be subject to kind of the random sampling here, right? And so we're going to get, right? So the lines get a lot more smoother, and over here, the lines get a lot more kind of tighter, right? So the analogy I like to use is imagine trying to draw a boundary using some kind of cable here. All right, so do I have a cable that I can use? All right, so here is on the, this is like, I don't know, some thick VGA or HDMI cable. It's pretty, like if I had to draw a boundary, it's like kind of hard to bend this cable here, right? And I would say this is like using a lower gamma, right? How quick and sharp of a turn can you make? Okay, with a low gamma, it's hard to make sharper turns. Okay. On the other hand, if I have a thinner cable here, I can make tight twists and turns here. Okay, and I would say this. We're not drawing cables here, but the idea is like with a higher gamma, we can make, you know, tighter turns, and we can really try to like thread the needle as far as where this boundary gets drawn between the red and the black points, right? So we're really able to get this, and we're even able to kind of get the exclave of I don't even know, like here it created a boundary that joins these red points together and stuff. Okay, lower gamma, we're getting something that, you know, separates that, and this is actually still doing a decent job of respecting the red dots kind of encroaching on the black points over here. Okay, whereas, you know, with the lower gamma, it says you know, this is kind of the best boundary I can do. Okay, what happens if I keep the gamma at 0.5 and I increase the cost? Okay, so this is cost 10, and this is cost 0.1. Okay, so what's happening here? So the gamma is kept at 0.5 here, and, you know, as we increase the cost, you know, here I have cost 10. Again, is this higher variance, lower variance versus cost 0.1? Higher variance or lower variance over here? Low variance, high bias, high variance, low bias. Which side is this? Low variance, higher bias over here. And then over here we have what? The opposite, right? Okay, but how would you describe the shape here? So here I'm keeping the gamma at 0.5. So this is still kind of like the tool I'm using to draw my boundary. So I don't have like the tight like squiggles that we get over here. Okay, right? I don't have these kind of tight turns that I have when gamma is equal to 10. Gamma is kept at kind of a lower value, but what we're seeing is that each individual point is able to kind of exert more force on where the boundary is, right? Each point is able to kind of exert a little bit more influence on where the boundary is, whereas over here it's like we're trying to bend this, like, you know, using our pinkies or something, and like how tight of a boundary can you form with this? Not super great. Whereas over here we're still have kind of this thick cable that resists making tight turns, but I'm able to exert kind of a lot of force to kind of to bend it to my will a little bit. But again, it resists making tight turns. Okay, And as I kind of alter this, here I have gamma at a higher value, giving us more flexibility. All right, and so even though my cost is low, I'm doing a decent job. And as I increase the cost, the overall kind of flexibility and kind of twistiness of this cable, forgive the analogy here, remains kind of similar, but where I keep gamma equal to 2. But again, each individual point is able to exert a little bit more influence on where these boundaries get drawn. So I have that. Here's gamma 5, and as I increase the cost with gamma equal to 5, we have this. Okay, so I would say explore these things and come up with some way to summarize the effect of gamma and cost parameters as far as support vector machines go. All of these things, just like we've been using kind of toy data sets here. And again, keep in mind what kind of variables you have in the first place, and ask, does it make sense to apply some kind of classification algorithm, a classification method here. All right, that's all I have for this lecture, and I think this gives you enough to kind of complete homework 4. Homework 4, you've got some coding up of KNN and some of your classification methods, naive Bayes classifier, and you'll just discuss a little bit of the support vector machine. But we'll wrap it up there. Let me give you your last view quiz answer for today. The last view quiz answer today is the letter A. A as in apple. A as in apple for your last view quiz answer. And with that, we'll go ahead and end our lecture here today. So have a good rest of your week, good weekend, and we will see you on Tuesday.